Now that you understand a little bit about the climate system and about forcings and feedbacks, let's apply it to the ocean. So why does the ocean move? Why doesn't the ocean just sit there? Well, you may be surprised to realize the ocean doesn't move nearly as much as the atmosphere does. The atmosphere gets heated up from the bottom. Just like boiling a pot of water, if you heat something up at the bottom, the warm fluid, whether it's water or air, is going to rise, spread out, and then cool and sink. And so you get entire circulation cells. That's why you see the water moving around when you boil it. The ocean is different. It's heated from the top, which makes it pretty stable. Sort of like packing for a big move. You have your lightweight stuff on top, your medium stuff in the middle, and your really heavy stuff on the bottom. But there are a few things that can disturb that. With ocean circulation, there are two things that we want to keep track of: the temperature of the water and how salty it is. Just like warm air rises, warm water rises. So if we just look at temperature in the ocean, we expect to see warm water on the top, cooler water deep down, and the coldest water on the bottom. And that is mostly what we see. But the effect of salinity makes it a little bit more complicated. Very salty water, water with high salinity, is dense. It sinks down. Water that's close to being fresh is buoyant. It rises to the top. And remember that sea ice albedo feedback we talked about? That has an effect on salinity too. When ice forms, it pushes some of the salt out of its way. Ice is all sorts of pretty crystals and a complicated lattice. There isn't really room in that structure for molecules of salt. So when sea ice is formed, that's the ice that's just formed by the freezing of the top layer of the ocean gets just a little bit saltier as a result. Now imagine that happening somewhere really cold, like the North Atlantic. You have ice forming, so your cold water that was at the surface gets salty. Now that it's cold and salty, it's going to be very dense, which means it's going to sink all the way down to the bottom. That's North Atlantic deep water. It spreads out from the North Atlantic and eventually makes it all around the world. Deep water can be formed in other places too. Antarctica actually forms bottom water, which sits even lower than deep water does. That's because it's even colder. The North Pacific isn't cold enough to form deep water, so it doesn't have its own source. You can think of these water masses traveling around the world with a little bit of a memory of where they came from. Water can only interact with the atmosphere when it's on the surface. So it gains its characteristics, like how much oxygen it has at the surface. And then we can track those water masses as they travel throughout the world. If you were to stand at a beach looking out at the Atlantic Ocean here in New York, you could see water moving. That water is on a 10,000-year journey around the world. Once water sinks in the North Atlantic, it spreads south throughout the Atlantic Ocean. Some of it will wrap around Antarctica, and some of it will go on a big loop through the Pacific. After it goes through the Pacific, it returns through a narrow strait, or rather a series of narrow straits in Indonesia. The water then loops around South Africa and returns to the Atlantic. Now, what I'm giving you here is a pretty idealized picture. If you followed an individual water molecule, you probably wouldn't see it make the whole route. What you would see is a lot of little random motions. It's only when you take a step back and look at the whole system that you can see these larger scale patterns. It can be fun to imagine what alien oceanographers would think. What if you came and looked at the ocean with no preconceived notions about how to orient your maps or what the important part was? Well, I think this figure shows something close to what you might come up with. Here we see that the ocean is basically donut-shaped. I know, you're not used to thinking about it that way, but it really is. The Southern Ocean encircles Antarctica, and that's where most of the action is happening. Off of that big donut-shaped ocean, we have 3 bays. That big one we call the Pacific, and then the smaller ones are the Atlantic and the Indian. This view of ocean circulation is also simplified. It's a model. Every version of ocean circulation is going to have to be simplified in some way. The trick is to get it simple enough that you can understand it, but complex enough that it still shows you the details that are important. I've told you how the deep ocean circulates, but that's not the ocean circulation that most of us are used to. We're used to thinking about the circulation that happens on the very shallow skin of the ocean, really only the top 100 meters. That's where you get things like the Gulf Stream. Those are surface currents, driven primarily by the wind. Those currents travel in circles, primarily, because of the Coriolis effect that we talked about earlier. The water would just move north and south from the equator, following its temperature differences, but it can't. It's on a spinning Earth. As a result, we get gyres, big circular flows within the basins. The centers of these gyres can be very calm. That's also where garbage accumulates. If you've heard of the garbage patch in the Pacific, and there's a small one in the Atlantic too, that happens because all of the surface currents pile water up in the center. Those surface currents are pushed by the wind, but they don't move directly the way the wind pushes them. If the wind pushes to the north, the first layer of the ocean will move to the north. But remember, the Earth is rotating, so it's going to be deflected just a little bit to the right. But now the layer underneath that is being pushed by that water that just moved a little bit to the right of north. That's going to be deflected even further to the right. That's going to keep happening layer after layer till we get the spiral, until at some point we come to the layer of no motion, where there just isn't enough energy to move the ocean horizontally anymore. The result of all that is that water gets transported more or less at 90 degrees to the wind. That's really important on the west coast of continents, or the east coast of the ocean basin, if you want to think about it that way. If you've ever tried swimming or surfing off the coast of California, you know that that water is cold. The reason it's so cold is that the winds push the water offshore. When water is pushed offshore, you can't just leave a hole in the ocean. What's going to happen is that cold water from underneath is going to upwell, is going to come to the surface. That's not great news for people like me who like to swim in warm water, but it's really good news for fishermen who live on the west coasts of continents. Once in a while, the cold water doesn't come as planned. You get an unusually warm current. For fishermen in Chile, a warm current around Christmas time meant a year of bad fishing. They named that current El Niño, after the Christ child, because it was Christmas time. Now we understand El Niño as a much bigger phenomenon, one that does not actually start at Christmas, that's not just about the ocean. It's about the way the ocean is connected to the atmosphere. The Pacific Ocean takes up about a third of the surface of the Earth. It's easy to forget how enormous it is. Winds blow across the Pacific, more or less from the eastern side to the western side. That means that water gets pushed along, that very surface water. It piles up in the west. Because the water is just sitting there all piled up, it gets warm, and we call it the Western Pacific Warm Pool. The cold water upwelling on the eastern side of the Pacific sticks out along the equator, and so we call it the cold tongue, because it kind of sticks out like a tongue. That's the normal situation for the Pacific. It seems unbalanced, I know, and actually the surface of the water is literally higher in the Western Pacific than it is in the Eastern Pacific, but only by a very small amount. Remember, all the maps you see have exaggerated scales if you're looking at the width of the ocean versus the depth of the ocean. So what happens when those winds get a little bit weaker than usual, or even reverse? Well, all that water that's been piled up in the west is just waiting to come sloshing back across the Pacific Ocean in something called a Kelvin wave. When that happens, this unevenness in the Pacific is flattened out. All of a sudden, instead of having warm water in the west and cold water in the east, you have kind of warm water everywhere. That might not seem like a big deal, straightening out the surface of the water in the Pacific, but it turns out that it has effects all over the world. During an El Niño year, a time when the Pacific loses its east-west differences, it gets rainier in the American Southwest. It also gets drier in places like Indonesia. You get droughts, floods, wildfires, changes all over the world, driven by what's happening in the Pacific. Now let's consider the opposite situation. What if those winds are a little stronger than usual? Well, when that happens, you're going to get even more water piling up in the west and even more water coming up from the deep ocean in the east. When that happens, we call it a La Nina event. The name La Nina is just meant to be in opposition to El Nino. During a La Nina event, there's more rain in the Western Pacific than usual. That can be bad news for people who live there because it can lead to mudslides. You also get drought in other parts of the world. So why are the effects of El Nino so widespread? Well, I told you that El Nino is a coupling between the ocean and the atmosphere. Sometimes you get Kelvin waves moving across the Pacific that aren't El Nino because the atmosphere isn't in lockstep with the ocean. But once they're moving together, that's a real El Nino event. We get rain wherever we have the warmest water. Think about it. It's easier for warm water to evaporate than it is for cold water to evaporate. And what goes up must come down. So the more water we have going up, the more water we're going to get coming down as precipitation. Wherever the Western Pacific warm pool is, that's where the rain goes. It might not be obvious, but what happens in the Pacific can control what goes on in the Atlantic. In addition to being scientifically important, El Nino events are really important agriculturally and economically. Being able to predict an El Nino event in advance is a huge advantage. You can tell farmers to plant less, to plant more. You can tell people what to prepare for. Studying ice can be one of the most exciting parts of oceanography. When I was in Antarctica, we got to step off the ship onto a layer of ice. It was incredible. You could stand, and you knew that there was just a little bit of ice underneath you, and under that, just ocean. Don't worry, the sea ice is pretty stable where we were, but it isn't stable everywhere. Sea ice is formed just when the surface of the ocean freezes. Remember, when water freezes, it spits out some of the salt, so sea ice is fresher than the water it comes from. But what about glaciers? Glaciers are land ice. Land ice and sea ice can look alike. In fact, they can even touch, but they have completely different backgrounds. Land ice is formed from precipitation, snow and rain. So it's fresh water, all the way fresh. When sea ice melts, people like me get concerned because it indicates that something is happening with the climate. But the melting of sea ice by itself doesn't have an impact on the height of the ocean. It has a really big impact for animals that live on sea ice, like polar bears. But what about people? We don't live on sea ice. Well, sea ice melting can be a problem because it indicates that warming is happening, and because of that ice albedo effect that I told you about earlier. The melting of sea ice can actually exacerbate global warming. But what about sea level rise? I told you that the sea level doesn't rise when sea ice melts, but it does rise when land ice melts. You can think of sea ice melting as a few ice cubes in a glass of water. As they melt, the water level isn't going to change. Land ice melting isn't like that. That's sort of like taking a big pile of ice and throwing it into your cup of water. It doesn't matter whether or not the ice is melted. What matters is that it's no longer on land. It's now in the ocean. That's what's driving sea level rise around the world. In 2002, there was an unprecedented collapse of an ice shelf called the Larsen B. An area the size of Rhode Island disintegrated over the course of just a few days. I was fortunate enough to go to that area a few years later to see what had happened. We don't know if this sort of event has happened a lot in the past or not. It is very difficult to study ice close to the land. That's because it's dangerous. Glaciers are constantly breaking, and it's pretty scary when you get close to that. So we have to use a lot of indirect methods to study the ice. One of those methods is putting hydrophones in the water. Hydrophones are just microphones that are adapted for use at sea. We can actually listen to the ice melt, and that can tell us what's going on distances that are really far away. Listening to ice melt might not sound exciting, but it allows us to get information we can't get at otherwise. Another thing we can do is put instruments on glaciers right now. The hope is that the next time there's a big collapse, we'll already have instruments in place. Remember, glaciology is a really new science. Oceanography has been around for as long as people have been trying to use the ocean to get from one place to another. But glaciology, the study of ice, is really just something that's happened recently. Now that we have satellite technology, we can see the extent of the ice and sometimes its depth. That means there are a lot of exciting new things to find out about the ice. But there's also a race against time. As more ice melts, we're going to lose some of the information that was in it, and we have no way of getting that back.